Let us consider in this video the notion of supremum and infimum. These are similar to maximum and minimum that we are more used to, but they're slightly different. So let's see what are the differences. So for example, let's say I give you the set, something easy, 0, 1, 3.5, pi 1/2, 5. And I ask, what is the maximum here? So the maximum in this set is clearly the number 5. It is the largest. And the minimum is the smallest, which is 0 in this case. Okay, so we are used to sets where we find, this is very easy for us, where we can find the value that is the largest and the value that is the smallest. And for example, we could have another example. Let me define the set A. We denote sets with braces. Okay, so the set A of numbers P, rational numbers P, such that P is positive and P squared is less than 2. Okay, so this is the set. Let me do a picture. So this is 0. And this is, so we have P squared less than 2. That means square root of 2 is involved. Okay. And we have 0 is out. Okay, and P squared less than 2 means that square root of 2 is also out. And then the rest, the positive P such that P is less than the square root of 2 would be, whoops, here. But actually it's not, I draw it like a line like this, but that's not quite correct, is it? Because it looks like all the numbers are there, but notice that I'm talking about rational numbers here. So actually, it would be more like this. The rational numbers, but remember, between two rational numbers, there is always another rational number. Okay, and in between those, there is always another one. So we will have so many that it will look as if it's a continuum, but we know it's not. Okay, it has gaps. Okay. So what happens with this set? Well, remember, square root of 2 is not a rational number, so it's out. Okay, and therefore this set A contains no largest element. Okay, so before we saw that in the previous example, the number 5 here was the maximum, was in the set. Now in this case, there is no largest element. This may or may not be intuitively obvious, so it requires a proof. For some people will be like, yeah, sure, but it does require a proof. So let's say we pick a very large rational number, smaller than square root of 2, and we call it P. Okay? So then we want to find some other rational number Q. Okay? In the set A that is in between a square root of 2 and P. We have seen something similar to this before. We remember when we were saying that in between two rational numbers, there was always another one. Now, the trick we used the two extremes, like the two extremes of the interval to produce another rational number. We cannot do that in this case. We cannot just take the midpoint between p and the square root of 2 because what happens? Square root of 2 is not a rational number. Okay, so if I take the midpoint between p and square root of 2 is also not a rational number. That's a challenge for you. See if you can prove that. Okay. So, well, fortunately, if you think about it for a little bit, the information we have here, we don't have that much information. We have this p squared less than 2. So that means that p squared minus 2 is negative. 2 minus p squared is positive. So we can involve that somehow and guess that our q needs to be a little larger than p. So we could decide to add to p some quantity that involves the p squared minus 2, which is negative. So we need to put the negative sign here. And after some tinkering, you will find that p plus 2 is convenient, okay? Because actually it simplifies very neatly to p plus 2 divided by p plus 2. So this is a guess. I'm eyeballing what the number could be that belongs to A and is in between P and square root of 2. So this is a candidate. Now we need to check that Q is in A. Okay, so for this we need to check that Q is rational, which surely it is, because it's a quotient of 2p plus 2 and p plus 2, which are rational expressions. Okay. It is positive. Indeed, because 2p plus 2 and p plus 2, those are positive numbers. Or if you want, looking at the first expression here, you could say that because p is positive, p plus 2 is positive, and p squared minus 2 is negative with a negative in front, then everything is positive. Okay. And then the last thing we need to check is that q squared less than 2. Okay, this means basically, well, you can write it as 2p plus 2 squared divided by p plus 2 squared less than 2. And this I leave for you to check. Okay, just expand everything, cross multiply, and check that what you have on the left is smaller than what you have on the right. Okay. So Q is in A. So what we have found is also, by the way, Q, I guess this is obvious, but Q is bigger than P, okay? Because P squared minus 2 is smaller than 0. Okay, so we did find a number, a rational number in A that is in between P and square root of 2. And now for this number that we have found, we could repeat the procedure and find another one and another one and another one, and we would get always a larger number that is in A. It's still smaller than square root of 2, and we can keep going on and on and on forever. Okay, so this means that A contains no largest element. Okay. We could, you see, we have maximum and minimum, so we could do something similar. Okay, considering the set B of rational numbers positive such that p squared is bigger than 2. Okay, in this case, well, in this case, we have 0 here, we have a square root of 2, and then what happens is that these numbers are bigger than the square root of 2. Okay, so they are here. Okay, remember, so many. In between 2, there is always another one. So it will look completely solid, but remember, it's not, okay? It's like a mosquito net. And then the square root of 2 is missing. Okay, in this case, this set B, if you notice, is open to the right, okay? It keeps going on forever. But in this case, this one has no smallest element. Okay, and the proof is similar to what we did for A, okay? So, one thing that we notice here when we look at the pictures, let me copy this picture. So this is A. Oops. So notice although A contains no largest element, when we look at it, it's not going on and on forever like B, right? It's it's bounded. So although it doesn't contain the largest element, A is clearly bounded above. Okay. By the way, B is bounded below, but it's not bounded above, okay, because it extends all the way to infinity. Now, I said it's clearly bounded above, but the mathematician in us should have jumped and said, well, that will be clear as soon as we define what that means, right? So let's give a clear definition. So definition, let's say S is an ordered set, okay, and let's take some subset E in S. This elongated C is like this, okay, means that E is contained in S as a set. Every element in E is contained in S. It's an element of S. Okay, so E is contained in S. I did the symbol a little exaggerated here, so that, but you get the idea. Then if there exists some element beta in S such that X is less or equal than B for all x in E, okay, we say that the T is bounded above, okay? And here, if we have that x bigger or equal than B, we say that it is bounded below, okay? So we have the two definitions at once. All right. So in our set A, we could have taken as a bound, you could have taken as a bound any value that is on the right of square root of 2. Okay, so this I drew here. We could take 1.5, for example. We could have taken 2. We could have taken 1.45. Any of these is an upper bound for A. Okay, you see what is happening here? What is happening here is that every element in the set B is an upper bound for the set A. And similarly, the symmetric statement is true for A. Every element in A is a lower bound for the set B. Okay. So again, looking at this picture, notice that for every bound that we take, every bound for A that we take is going to be to the right of a square root of 2. And it's going to be a rational number because it needs to be in S. That may have gone a little unnoticed here. Notice that the bound has to be an element in S. So if we are taking our set A that is a set of rational numbers, then the bound has to be a rational number. So it's not okay if someone says, well, square root of 2 is a bound. No, that one is outside, okay? So we can only take rational numbers, and we can only take rational numbers that are to the right of square root of 2. So whichever one you pick, we have seen that we can produce a slightly smaller one, and a smaller and a smaller and a smaller, always to the right of a square root of 2. So again, that means that every element in B is an upper bound for the set A. B is the set of all upper bounds for the set A. Now, this means that there is no least upper bound for A. There is no least upper bound for A. Okay, this is because whatever upper bound we choose, which has to be an element of B, okay? An element of B, we can always find a smaller one. Okay, and this connects with the definition of what does it mean? A least upper bound or a supremum. Okay, so let's go there. Definition. As before, let's take S ordered set. Let's take a subset of S. And let's assume E is bounded above. Okay, now suppose there exists alpha in S, an element alpha of S, that satisfies the following two properties. So first, alpha is an upper bound of E. And the second is that if, let's take now gamma is less than alpha, then gamma is not an upper bound of E. Okay, so we have an upper bound that such that whatever number gamma we pick that is smaller than that alpha upper bound, that gamma is not an upper bound. Okay, when this happens, then alpha is called the least upper bound of E. Okay, and notice from property 2, we have that there is at most one of these. Okay, all right. So then this we also call the supremum of E, and we denote alpha equal the supremum, alpha equal the supremum of E. Okay, similarly, we have the greatest lower bound. Okay, this is the infimum. And we would say alpha is the infimum of E. Okay, with the upper paid adjustments.